Just observe this page number. In order to solve this problem, that is July 2019 question paper, 75 page number on, that is IS code book page number 75. I am going to use this formula here, that is equivalent shear. See, whenever beam is subjected to bending as well as torsion, so there will be shear has to be calculated like this. Earlier, what was the formula? VU. Without shear, it was VU. So whenever there is a torsion is also acting on the beam, the equivalent shear force we have to calculate. You can say this is VE. For this VE, we have to design shear reinforcement. So you can see one term is additional. 1.6 TU by B is additional, where TU is the torsion which will be given in the problem. The value of TU will be given in the problem. Now, one more formula that I'm going to use here is page numbers, same page number, that is equivalent bending moment. See, the way equivalent shear is calculated, which includes the effect of torsion here. Similarly, equivalent bending moment is also like that, which includes the effect of torsion. Second term. Second term is the moment produced due to the effect of torsion. So where mu is bending moment at the cross section, it may be WL square by 8 or something like that. Second term is MT. MT is the moment produced due to torsional effects. So TU into 1 plus D by B by 1.7. That is what is EMT. Finally, I will use this formula. In order to use this formula, in this formula, my aim is to calculate the spacing. Observe this one, which is SV. My aim is to find. So how I have to decide the diameter of the stirrups. Let us say I will go with two-legged 8 mm diameter stirrups. So this is fixed 2 into pi by 4 into 8 square. So in the RHS part, everything you will be knowing except SV value. SV is the center to center distance between the stirrups. So using this formula, I am going to find out the stirrup spacing, assuming a suitable diameter, means 8 mm usually, 8 mm 2 leg. Sorry. So this is what I'm going to make use of. It is directly it is taken from a question paper. Page number 75 should be referred for solving this problem. This is the page number 75. So let us start this example here. Now observe this. See, before I start this one, observe how this question paper, the person who sets the question paper, what he thinks about this module, how to set the question paper. What is done here is observe here. What is the how the person who is setting the paper thinks about this module. What type of questions he has the choice here. One is I can say like this. Singly reinforced and okay, it will be like this. Observe how the mind of the examiner works. Singly reinforced design of singly reinforced beams. Okay. One more is, as you know, it is doubly reinforced. But he has to set two questions here. So how it works, you just see. Second choice is doubly reinforced. In this one, he can set 4 questions. How it is? He can set a problem on singly reinforced cantilever beam or singly reinforced simply supported beam. If it is cantilever, you cannot use WL square by 8. You have to use WL square by 2. If he says it is a cantilever. Similarly, doubly reinforced beam, which is simply supported, or doubly reinforced beam, which is a cantilever beam. So one can design doubly reinforced cantilever beams, doubly reinforced simply supported beams. The only change will be in case of cantilever, steel is at the top. Okay, steel at the is above the neutral axis. And one more is its bending moment is WL square by 2. And span by depth ratio is different if it is cantilever. I'll be giving you the solution for that also. And this is what he thinks when he wants to set a question on this module. One more choice he has is he can set a problem on beam with the second question out of module 3. In the module 3, there will be 2 questions. In that one, in most of the cases, what they are doing, they are setting a second problem as something related to beam with torsion, which is easier than first one. In this question paper, if you see, in this 2019 question paper, if you see this one, you are going to find that this problem is easier. Easier means it takes less time than solving a doubly reinforced beam. That is why in the examination, if you are able to solve both the questions, that should be the strategy here. In the exam, you should think which one will take less time. That way you should go. You cannot use the choice and all. So in this module, you should ask yourself these questions. Is it possible for me to design a singly reinforced, simply supported beam as well as cantilever beam? Is it possible for me to design a doubly reinforced, simply supported as well as cantilever beam? Like that, you should solve 2 examples here, 2 examples here. One is simply supported, one more is cantilever. Next question you can ask yourself is it possible for me to design when the beam is subjected to combined bending and torsion? If that is the choice, usually if you are good in all this, in the examination, when you find that this problem is there, everybody will try this one only because it is going to take less time. How it is, I will show you. How it takes less time, you can see here. See this one. The problem is given here. A rectangular beam 230 by 550, capital D is there, is subjected to a sagging bending moment of 40 kN. So instead of asking you to find WL square by 8 and all, directly the value is given. See, instead of giving span and asking you to calculate loads and all, directly MU is given in the problem. Shear force is 30 kN. VU is given directly. And a twisting moment of 11.5. Twisting moment is nothing but torsion. So all these 3 values are given. Design the reinforcement and sketch the details. Use M20 and Fe415 steel. The only change that you may get is they may ask you to use Fe500. Okay. Now observe this one. As I told you, step number 1 is find out equivalent bending moment and equivalent shear. Refer page number 75. Here, referring page number 75, you are going to get this formula there. Simply substitute the values. MU 40. TU is given. Twisting moment 11.5. So 11.5 is TU. Then 1 plus D is 0.55 meter, 550 mm. Divided by B, 230 is 0.23 meter. Divided by 1.7. So you will get 62.97 into 10 raised to 6. Actually, the answer that you are going to get is in kilonewton meter because all values are in kilonewton or meter. Just put 10 raised to 6 Newton mm. Now find out MU limit 0.138 FCK BD square. In the problem they have not given the value of This is what you should understand. If this can be 25 mm also, see here. Assume d minus 25. That means this is what is the usually a student is getting confused. If it is not given, the examiner has to give marks for whatever the student assumes. Observe this. Let us say this distance, if it is not given, or total is given 550, they are telling capital D. In that 550, you must get a small d now. If this is not given, you can use either 50 or 25. Normally 25 is used actually. Anyway, let us see that one. If somebody uses 50, let us say, if it is not given, it becomes 500 mm. Okay, small d becomes 500. Otherwise, what will happen? It becomes 550 minus 25. It will be 525. So the person who evaluates your answer sheet, if this is not clearly given and if the student assumes 50 or 25, he has to give full marks only, because it is a problem with the paper setting. Data is not clear, but student can assume 25 or 15, no problem. So what is done here is, observe, in this case I have calculated equivalent bending moment using mu plus mt. These formulas are there, 62.97 into 10 raised to 6. Simply I used 75 page number. Then I will just calculate mu limit. So this mu limit should be more than this value. Whenever they set a problem on torsion, it will be under reinforced only. They cannot give you double reinforced sections. That can also be solved, but usually what they do, now you will see this one. Now mu limit will be more than this. You calculate this one. See this one here. It is 158.7, which means mu limit is more than equivalent total bending moment. So it means mu limit is higher, means it is section is under reinforced. So this is what you need to check here. Once this is done, find out equivalent shear force. Again, it is taken from page number 75, VU plus 1.6 into TU by B. Substitute all the values. Okay, 110 kilonewton. This is the end of the first step. In first step, I have used the formula given in page number 75. I am able to find out equivalent bending moment and equivalent shear. Now step 2 is like this. Reinforcement and side face reinforcement. This is what is important here. First time you are hearing this particular word, side face reinforcement. This is not usually considered if there is no torsion. Now, what is side face reinforcement? Side face reinforcement, this term comes only if the beam is subjected to combined torsion as well as moment. Now, these are the usual positions of the steel rods in case of simply supported beam. These are hanger bars, these are main bars. Now, side face reinforcement means because of the torsion, I should provide steel rods here also. How to calculate this? I'll show you later on. If you observe the rods, I mean steel bars here also, which are tied to this, these bars are running parallel to the main steel and they are tied to the stirrups. So this is what is called a side face reinforcement. This is required to resist the torsional effect. Now I'll calculate AST by whatever formula I have given in the notes, as well as SP16 also I'll do it here. Observe. You can see how fast you can do if SP16 tables are used. AST is equal to 0.5 FCK BD by FY 1 minus square root of 1 minus mu, where mu is 4.6 MU by FCK BD square. Now observe here. How I have calculated this one. After writing this formula, what I will say, I will calculate FCK BD. I will not do any calculations here. I will start with FCK BD 20, 230, 500. Okay, I have assumed it as 50 mm now. Effective cover is 50 mm. Effective cover to the tension steel is, so 550 minus 50. So 230 FCK BD is a term I have calculated, 2.3 into 10 raised to 6. Now what I will do for mu calculation, after this one I'll calculate mu. So 4.6 mu by FCK BD square, 4.6 mu. See this one, bending moment, equivalent bending moment, 62.97 into 10 raised to 6. Now what I will do, FCK BD square, I will substitute this one, again multiply by D, because it is D square, whereas this is FCK BD. So I'll write 2.3 into 10 raised to 6, one more 500, because this is D square. D is already there in this 2.3 into 10 raised to 6. So I end up 0.25 number. So what I will do here is, observe this, I'll substitute in the formula. I'll write 0.5, which is there in the formula. FCKBD is required here again. Now what I will do, this value again, I'm going to use it. It means 2.3 into 10 raised to 6. Here it is required one more D here in the denominator, but here it is 0.5, 2.3 into 10 raised to 6. Divided by 415, 1 minus square root of 1 minus 0.25, because mu is 0.25.
Okay.
371.32.
Okay.
So this is the calculation of AST. Check it for minimum steel. Now I'll show you this same calculation, how it can be done using SP60. Observe this. It will be very fast. Once you are used to SP16, you don't have to use that formula. Now, or use SP16 table 2, page number 43. Now, SP16 table 2 means you have to calculate mu by BD square. That's all. See this, it is very fast. Use this method and find AST. It will be very fast. I'll show you here. Instead of this formula, which got me 371.32, I'm going to use SP60. Now, mu by BD square, this term I have to calculate, which is 62.9 into 97 into 10 raised to 6 by BD square. I end up with 1.095, which is very closely equal to 1.1. Now 1.1 I'll check in table 2. Let me check whether it is there or not in this. The table I have to refer. That's all. Yes, I think it is table 3. Table 2, observe this. So first you can calculate AST without wasting time. I have calculated this term mu by BD square. As I told you, table 2 is used because FCK is given as 20. Since FCK is 20, I am using table 2. I have calculated mu by BD square, which is 1.1. See this green color. 1.1. I don't need to interpolate now, because 1.1 is whatever I have calculated, mu by BD square. Then I'll go under this column Fe415. So under Fe415, I am getting 0.327. This is PT value. I got PT. So once I know PT, AST by BD into 100 is equal to 0.327. From that, I am going to get AST value. So this is how it is done. It is very fast. Faster than that formula. You can mute it. All of you, you can mute your this one. Huh? Okay. Next is this formula. I am no need to use. If you practice this one, see, this is what I have done. 0.327. I was showing PT. Now PT is equated with AST by BD into 100. From this one, extract AST. So AST is 376. Very close number. Close number with respect to this formula. This has given me 371.32 using this time consuming formula 371.32. I am getting 376, slightly higher number. So once this is calculated, check for minimum steel. Check for minimum steel. AST in any case should not be less than this formula. So 0.85 BD by Fy. So 0.85 BD by Fy is checked here. It is 235.5. So I'll go with 376 because out of these two, this one is more. If this value was 400, let us say, I have to go with this value. Because in any case, the value should not be less than this formula. Okay. So it means out of these two, 376 is higher. I'm going to use 376. So I'll use 12 mm bars because area is very less. Using 12 mm rods, number of you can see you can mute your just mute it, otherwise it is creates disturbance. Now what I will do here is area of total area by area of one bar, which is 3.32. Say 4 bars I will provide. Now actual AST is 4 times 5 by 4 is 452. Okay. Then important is side face reinforcement, which is not there in without torsion problems. Side face reinforcement is 0.1% of gross area. So 0.1 by 100 into B into D, gross area. Gross means capital D. So this is 230 into 550, 126.5 square. So this is the extra thing that you are getting here, apart from many other revised formulae. Okay, this is also an extra thing. 126. Now you can see this. I'm going to choose bars for side face reinforcement. Total area that is divided by area of one bar, that is 2 bars. Now observe this. What is this 2 bars here is side face, which is required for taking care of torsion. So what I will do is 2 bars. This is 2 bar means here and here also like this. So this is side face reinforcement. Here 2 bars means on each side 2 bars I have provided. So design for shear reinforcement. So already I have calculated equivalent shear force in the step number 1. Equivalent shear force. Equivalent. It is here. Already I have calculated equivalent shear force. This equivalent shear force includes the effect of torsion also because one extra term has appeared. So that value is 110. So you have to find out the shear capacity and all. Same thing, everything is same now. That is except this formula. Now see here. Actually, the factored equivalent shear force is 110 kN. You have to check whether the concrete with main bars itself is sufficient to resist this or what. So find TOSI BD. And it is same procedure. TOSI BD. TOSI, it depends on the percentage reinforcement PT by M20. So usually when you reach here, there will be some confusion. For example, PT, I have provided 4 bars actually. 4 bars of 12 mm diameter. Corresponding to that, you have to calculate here. But usually in the examination, what is happening? Whatever PT you get it, same can be used. Both are, there is no, because the value of TOSI will not change for that slight variation. So PT 0.39 M20. So using table 19 corresponding to these two numbers, TOSI is 0.42. Now once you find TOSI, I can find out the shear capacity of the beam without stirrups. So VUC 0.42, which is TOSI. Here you can see 0.42 into B into D. So 48.3. whereas it has to resist 110 kN. Out of that, Without stirrups, the beam is capable of resisting 48.3. It means the difference between these two values, 110 minus 48.3, that difference has to be resisted by stirrups. So for that one, you have to use this revised formula. Revised formula, as I already have showed you, it is page number 75 only. All formula for torsion are on a single page. So you have to, from this one, you have to find out just spacing, because ASV, you see this one, ASV, LHS, once you say I'm going to use 8 mm two-legged stirrups, this is fixed, 2 into pi by 4 into 8 square, this is fixed. TU is given, VU both are this one. Then you substitute all these values except SV, everything else is known to you. From that one, you have to find out, SV value. So that is the end of your design. No need to check for any deflection or anything. Unless it is specifically given. In this paper, they have not asked for check for deflection. If check for deflection is there, we can do it as usual. Okay. Check for deflection I have done for one problem. For every problem, the pressure is same. So that because check for shear means already we have done it. Shear design is done. So this is how you can design for beam subjected to combined bending and torsion. Any questions are here in this design? Any doubts are there? This is the end of your this one. So I'll be giving you some. I'll be giving you some assignment two. See what I am doing in case of assignment two is whatever problems we are expecting for the final examination, those problems I will be setting as assignment two for this module. I may give one problem on design of shear also, shear design problem. So if you just solve those problems, I think you can attempt questions of module 3. In that way, the assignment will be given. I'm going to set a problem on this type also, torsion also. Torsion, double reinforced beam design, single reinforced beam design, and cantilevers. Cantilevers along with the solution I'm giving. You just go through that one. If there is any problem, again, we'll discuss it for half an hour. Same thing. Only thing is WL square by 8 becomes WL square by 2. VU becomes WL. VU becomes W into L. Formula is different. Otherwise, rest all is same. Everything is same. So, any questions are there here? This is the end of your module 3. Module 3 end means if you can solve the assignment problems, you can be confident. On your own, if you can solve, first try on your own only. Don't try to ask anybody. Try to solve on your own. So, any questions are there here? I already told you that it is not easy to understand the torsional effect on a beam. For that one, I'll give you the notes. Even though it is out of syllabus, if you want, we can read that one. Whatever is there in the syllabus, using page number 75, it becomes very simple. If you see how the torsion actually affects, I'll share one somebody else's video actually. You can see that one later on. So this problem I have solved here. You can see this problem I have discussed here. This problem was analysis type of torsion problem. Today what I did was design type of torsion problem. So this problem also you should be able to solve. They may set this problem also. In the second test, I am going to set problems on torsion also, along with design of beams and slabs. So from Monday onwards, design of slabs I will start. See, any notes is missing. You can specifically tell me, I'll just give that one. Or else I'll tell you what should be read. What should be read means I'll just say that page only. If anything is missing from the syllabus, notes or problems. So this is the problem you can see in the previous class. What I have done here is, once again I will show you. M20 FE500 is used. Everything is given here. Only thing is that they should have placed two bars on either side in the problem, but they have given equivalent. That is, when VU is equal to 0, VU is equal to 150, VU is equal to, three cases are given. So because of the stirrups and spacings are given here, you have to find out like this. See this. I have calculated in the analysis problem TU1. Why I am calling it as TU1 is for case 1 when VU was 0. It is an impractical case. VU cannot be 0. As long as there is even a single load is there, VU will come into picture. Case 1 is impractical actually, but just to make you understand the formula, they have done like that. If VU is 0, what will happen to this formula? The second term will be 0. VU is 150, second case, everything will be there. You are trying to find out TU in this formula, try to analysis it is. What you are trying to find out here is in analysis problem is TU value. Rest all you know it. Rest all is given from the figure. You can make out everything else. Okay, this is what I have done in the previous class. There I calculated only TU1, TU2, TU3, three cases. Similarly, I'm supposed to calculate MT, second term of equivalent bending moment formula. Second term is MU plus MT. So in each case, MT has to be calculated, but I have calculated only for TU1 case. When TU1 is calculated, substitute TU1 here, find out MT1. So you have to calculate TU2 and TU3. Now if I ask you to find out TU2, what you will do? Simply substitute 8.68 in place of 17.02. If I want you to calculate TU3, just remove this 17.02, substitute 5.9, you'll get MT3. So this is the end of your module 3. If there is any doubts in cantilever beam designs, I told you WL square by 8 becomes WL square by 2, VU becomes WL, span by depth ratio will not be 20. Just remember these three. Span by depth ratio will not be 20 as 15 to 20 we write it. That is different. I'll give that notes and all. Solved. I have my own notes are there. Somebody is asking the theory notes also. So theory notes, it is a 100-page notes is there. Somehow I will try to share it. Handwritten theory notes are also there. You see, don't worry about the notes and all. Try to understand the topic first. All the notes I'll give. So this is your end of your module 3. I'll give some assignments. On your own, if you solve those assignments, you are safe in this subject. So now we'll take